All right, let's get started. So we're picking up right where we left off with the expansion of the Einstein equation. So we'd ended with this formula for the Ricci tensor in terms of the background metric and these corrections to the Christoffel symbols. And this is a covariant derivative with respect to the background metric. And the corrections to the Christoffel symbols had this form, basically just derivatives of the metric perturbation. Now the first thing to notice here is that if we just replace this exact metric or exact metric inverse with the background metric, then that gives us the leading order approximation. This is already linear in h, so any correction to this is going to be order h squared. So this is the leading approximation for C. So if we take this, plug it back in here, we see that this term is order h squared, because each C is at least order h. So if we want to pick off just the linear approximation to the Einstein equation, well then we just need this first term and the second term. Okay, so we're denoting the linear piece of a quantity with this delta, this linear variation. So this doesn't depend on h, so this gives you 0. The background covariant derivative doesn't depend on h, so you can pass this operator right through it. And so you just have covariant derivative of the linear piece of C, which was the correction to the Christoffel symbols. So if you plug this formula in, what you get is a sum of different second derivatives of metric perturbation h. So there's 6 of them. Because there were 3 terms here, and then you're taking the anti-symmetrization, so you double the number of terms, and a couple of them cancel. Mu. All right, do I have 6 terms written down here? 1, 2, 3, 4, 5. No, I'm missing one. There we go. There's the 6 terms. And these two I've written right next to each other. Cancel. So the reason they cancel, this is nu, mu, this is mu, nu. So they don't cancel by themselves, but they cancel once you contract with this g. Because once you contract with a g, it doesn't matter which order nu and mu are in. So then you just have these top 4 terms. I'm going to combine them down to 3 terms. So this box is the D'Alembert of the background spacetime. So it's second covariant derivative contracted with the background metric. And you can see that's coming from this term right here. This, what I'm calling H, is just the trace of the perturbation. So this term is coming from this term here. And then there's one last term. It comes from those remaining 2 terms there. Okay, so this is pretty simple. I'm going to make it look a little bit different by commuting these 2 derivatives. So I can write this as derivatives of the opposite direction plus a Riemann term using the Ricci identity that we worked with yesterday. So if you commute those derivatives, then what you find is still have this wave operator at the beginning. Now you have some curvature terms. So we've got a Riemann tensor there and a Ricci tensor here. Now I'm introducing this quantity h bar. So h bar is h bar alpha beta is the trace reverse of h, so it's h alpha beta minus a half g alpha beta g mu nu h mu nu. It's called the trace reverse because if you take the trace, you find that the value of the trace of this is minus the value of the trace of that. Okay, so this is the Ricci tensor, or the linearized Ricci tensor. And it seems like going from here to here, I've made things more complicated rather than simplifying things. But you'll see why in a second. So what we want is not the Ricci tensor, but the Einstein tensor. So this is the calculation that was on the exercises yesterday. We want the linear piece of the trace reverse of the Ricci tensor. So here, you get the linearized piece of the Ricci tensor minus the linearized piece of this product, which gives you 3 terms. So h alpha beta is just the linear piece of G. And now we have a background Ricci term. We could, if you want, put tildes in all these to indicate that we're taking the linearization of the full space-time. Okay, so then we have these final 2 terms. And now I'm going to make a specialization to a vacuum background, which will simplify the form considerably. So specializing to vacuum background spacetime, we have that the Ricci tensor of the background is 0. And so then this term is 0, and this term is 0. And you're just left with these two terms. So the explicit result, I'm now going to write entirely in terms of this trace-reversed metric perturbation. And as Luke noted, the trace-reversed metric perturbation is basically his h. So my h bar is his h, up to a minus sign, I think. And up to the fact that his h is always a perturbation off of flat space. This is a perturbation off just a generic background spacetime. Right. Last term here. Okay, this still looks more complicated than the Ricci tensor I started with, which makes it seem like I've done the wrong kind of manipulations in introducing this Riemann term. But the idea was to get everything in terms of missing index here, in terms of divergences of h bar. So this is a divergence of h bar here, and this is a divergence of h bar here. And we're going to set those to 0 in a second. Okay. Now you can do all this to second order following exactly the same procedure. So same procedure, but now just keeping quadratic terms. I'm not going to go through the calculation because it gets long. But you can get delta squared r alpha beta just by looking at the quadratic terms in r tilde alpha beta over there. So you get these by looking at quadratic terms in the exact metric, the exact Ricci tensor of the exact metric. And then you have the delta squared g alpha beta is just delta squared of r alpha beta minus a half g alpha beta g mu nu r mu nu. So you again pick off the quadratic terms here. And what comes out is delta squared r alpha beta minus a half g alpha beta g mu nu delta squared r mu nu minus a half h alpha beta g mu nu delta squared, just delta r mu nu plus a half g alpha beta h mu nu delta r mu nu. Okay, so here I'm dropping terms that are just proportional to the background Ricci because we're setting that to 0. And this is all in terms of delta squared r alpha beta, which is given by a very long, ugly formula. Why there's not the tilde? Oh, you mean here? Where am I going? Because I'm taking the linear piece. So the linear piece of this is h. And if you have another h there, that's a quadratic piece, it's not a linear piece. So you always just take, if you're looking for the linear piece, you're only taking, you can only get one h, and the rest has to be background quantities. Yes, so when we're looking at the delta squared, that's why here you have things like this, h times delta r. Yep. Okay, so I'm not going to bother writing down all these terms, because that would take a couple minutes. But just the general structure, what you have. So you have derivatives of h times other derivatives of h. You also have things like h times second derivatives of h. And a bunch of other things. But they're all of this form. They're all either derivative of h times derivative of h, or h times second derivative of h. That's the structure that occurs in all the terms. Okay, so if you want to see the whole expression, you can just look it up in any number of papers. But now I'm just going to continue on schematically to look at the form of the Einstein equation. Okay, so we now have an expansion of the Einstein equation to second order in h. So the zeroth order term is just the Einstein tensor of the background. We're working in vacuum, so that's 0. Then we have the linearized Einstein tensor constructed from h as given over there. And the piece that's quadratic in h as given almost over there, plus things that are of order h cubed. And this whole thing is 8 pi t alpha beta. So far we've been working with the exact h. We haven't actually input our expansion in powers of epsilon. We're just writing the metric as g plus some function h. So now let's put in our Taylor series. So this h alpha beta was epsilon h1 alpha beta plus epsilon squared h2 alpha beta plus order epsilon cubed. So remember, the reason why I'm doing everything to second order was at the beginning I said to model Emery's accurately enough for Lisa, we need everything to second order. Okay, so this is an expansion of the metric. Let me assume there's a similar Taylor series for the stress energy. Okay, so when I put this into this formula, well, first I get a term that's just the linearized Einstein tensor constructed from h1. Then I also get a term that's the linearized Einstein tensor constructed from h2. Then over here, I would have the quadratic piece of the Einstein tensor constructed from h1. And because that comes, each one comes with an epsilon, that's order epsilon squared. I won't need the things that are h1 times h2, because that would be epsilon cubed. So the general structure we have is epsilon times the linearized Einstein tensor constructed from h1 plus epsilon squared times the linearized Einstein tensor constructed from h2 plus this quadratic term, delta squared g, constructed from h1. And that's going to be equal to epsilon t1 alpha beta plus epsilon squared t2 alpha beta plus order epsilon cubed. So there's also an order epsilon cubed on the left-hand side, but I've just moved that to the right. Okay, so here I'm working with strict Taylor series, power series in epsilon. That means all the coefficients here are independent of epsilon, and that means that I can equate powers of epsilon on the left-hand side and right-hand side. So delta G alpha beta H1 has to equal T alpha beta 1, and this combination of second-order terms has to equal T2 alpha beta. So then we get a sequence of equations. Delta G alpha beta H1 is equal to 8 pi T alpha beta 1 delta G alpha beta H2. And now I'm going to move this quadratic term over to the right-hand side. So it's 8 pi T2 alpha beta minus delta squared G alpha beta of H1. So the idea is you can solve the first order equation, the linearized equation, for H1 given T1. So then you know H1, you can then plug it into the right-hand side of the second order equation, and then you know the source on the right-hand side. Then you're again just solving a linearized equation. This is just a linear operator acting on H2. So you're solving a linearized equation, but now with a different source than what you had at first order. So you're solving a sequence of linear equations, and you can carry this to arbitrary order. You always just have a source constructed from combinations of lower order perturbations. Okay, so I wanted to show you the general structure through second order, but for most of the lectures, we'll just be focusing on first order. So the next topic, still working in general perturbation theory, not restricted to Emery's. The next topic is gauge freedom in perturbation theory. So before I move on to this, are there any questions about just the derivation of those two equations? No? Okay. So one of the exercises was to show that delta G alpha beta is invariant under a gauge transformation. If you perform a gauge transformation of H1, you get the same value of delta G alpha beta. But certain gauges are much more convenient. They give you a nicer looking equation, and then you know your result is going to have exactly the same information as you would in any other gauge because it's a gauge invariant equation. So we want to pick a gauge that simplifies the form of this equation. Okay, so what do we mean by gauge transformation? In perturbation theory, what we mean is an infinitesimal coordinate transformation. So you can actually define these gauge transformations without referring to coordinates at all, but I think it's simplest to explain just using coordinates. So this means you take your coordinates, you transform them to some new coordinates. So x goes to x prime. And these new coordinates are almost identical to the old coordinates, but they differ by something of order epsilon. So we have some gauge vector xi that we can specify freely. We can make it any function we like. So how does this impact the metric perturbation? Well, let's look at the full metric in the new coordinate system. We can just use the standard tensor transformation law. And the idea is to now perform an expansion using this and using the expansion of g tilde to figure out how the first order term, h, or h1, how that changes under this gauge transformation. Okay, so in here we need the derivative of x with respect to x prime. So I need to write x as a function of x prime. That means I just move this over to the other side, and then I have x equals x prime plus epsilon xi. So we've got x mu prime plus epsilon xi mu. And we'll drop higher order terms. Then over here we have ddx beta prime of x mu prime plus epsilon xi mu. And now we want to put in coordinate transformation inside the argument of g tilde. So g tilde of, within indices mu nu, it's a function of x gamma prime plus epsilon xi gamma prime. And then we're dropping things of order epsilon squared. So now we just want to expand all these terms out and see what we get. So when this derivative acts on this first term, we get 0 if alpha is different than mu. We get 1 if alpha is equal to mu. So that's just a Kronecker delta. So we've got delta mu alpha plus epsilon times the alpha derivative of xi mu. And then get another Kronecker delta mu beta plus epsilon times the beta derivative of xi mu. And this is all multiplied by this. So now I'm going to do a Taylor series in this, expanding out the argument. So here we have g tilde mu nu evaluated at x gamma prime plus epsilon times xi gamma times the derivative of g tilde now everything's a function of x prime. And these derivatives are all derivatives with respect to the primed coordinates. Okay, so multiplying all this out, we get g tilde back. And this term here multiplies the two Kronecker deltas. We just have the original metric, but now as a function of x prime rather than of x. And we have a bunch of linear terms. The derivative of g tilde along the vector xi plus derivatives of the vector xc multiplied by the metric Now you might already recognize what this is, but I'm going to do one more step, which is substitute that g tilde is the background g plus epsilon h alpha beta. So for the next few lectures, h is going to just mean h1. So just to avoid writing that 1 over and over again, we're not going to have second order perturbations for quite a while. So h here is h1. So now we have that g tilde prime is g alpha beta plus epsilon times h alpha beta. Now, this whole piece is already multiplied by epsilon, so here I can just replace g tilde with g, because the correction is higher order. So we have h alpha beta plus xi gamma, partial gamma, background g, plus the derivatives of the background g, or sorry, derivatives of the gauge vector times the background g. Now, does anyone recognize what these three terms can be written as? What's that? Exactly, Lie derivative. So what we have here is that g tilde prime, alpha beta, is equal to g alpha beta plus epsilon times h alpha beta plus the Lie derivative along c of the background metric. So this is the linear metric perturbation in the new gauge, in the new coordinate system. So this we can call h prime alpha beta. And we see that it differs from h alpha beta just by the Lie derivative of the background. Now usually this Lie derivative of the background is written in terms of covariant derivatives. So to do that, we just note that the Lie derivative of a tensor is identical to what we have over here, but just replacing the partial derivatives with background derivatives, or sorry, with covariant derivatives. Now the covariant derivative of the background metric is 0. And you can bring this metric inside of the covariant derivative and bring this index down. Do the same, bring that index down. So this is just grad alpha xi beta plus xi beta, sorry, plus grad beta xi alpha. And this is usually the version that people will work with when doing a gauge transformation. Okay, so as we saw in the exercises, delta G alpha beta of this thing is identically 0 if the background curvature Einstein curvature is 0. So that implies that if delta G of h is equal to 8 pi T1, then delta G of h prime is also equal to 8 pi T1 alpha beta, because this additional term in h prime just contributes 0 to the Einstein equation. Now, a comment on why you have this condition. So I've written here where you have a derivative of the background metric is really a much more general result, or comes from a much more general result. So in general, for an arbitrary tensor, with arbitrary indices, if that's given by an expansion with a 0th order term plus a linear term plus higher order things, then the gauge transformation delta t 1 alpha beta, so the change in T1 under gauge transformation is just given by the Lie derivative of the 0th order term, which is exactly what we have here. So this is completely general. It doesn't depend on the fact that we're using the metric. It's true of any tensor. So what that means is, if the Lie derivative of t0 is equal to 0, then t1 is invariant. Under a gauge transformation, if this is 0, you don't have any change in T1. And this is easy to extend to arbitrary order in perturbation theory. Yeah. So yeah, if the background is vacuum. What's that? I'm saying that this is just a consequence of a very general rule. That the linear perturbation in any tensor, it doesn't have to be G, any tensor, is gauge invariant if the 0th order term is 0. Right, so if T0 is 0, then the Lie derivative is also 0. And so the Lie derivative of the Einstein tensor, the background Einstein tensor is 0 because this is 0. Yep. Okay, so now let's use this freedom to change the gauge to write the Einstein equations, the linearized Einstein equations, in a simpler form. So that's a gauge in which these divergences of h bar, which we had popping up all over the place, are just 0. So if we go back to our explicit expression for delta G, and put in that gauge condition, what we get is minus a half times the box of h bar alpha beta plus 2 times Riemann curvature so it's a fairly simple expression for the linearized Einstein tensor. Okay, how do we know we can always impose this? It's a fairly simple calculation to show that. Let's say we're starting with h in some old gauge, h old. So it's any gauge, doesn't matter what it is. And we want to transform to a gauge where this is satisfied, the divergence of the trace reverse is 0. Then we want h old plus this symmetrized derivative of a vector to satisfy the Lorenz gauge condition. Let me call this h nu. So we want h nu alpha beta to satisfy, keep it like that, h bar nu alpha beta divergence is 0. So that's just going to impose a condition on that vector xi. And we'll find that we can always find a vector xi that makes this condition hold. Okay, so the divergence of h nu is the divergence of h old plus, actually no, let me first undo this trace reverse. Derivative of h nu alpha beta bar is divergence of h alpha beta nu minus a half g alpha beta g mu nu h mu nu and now let's substitute what h nu is in terms of h old and the vector. Let me write one more line to simplify this. So this covariant derivative passes through the background metric to act on h nu, and then this g just brings that up. So we have minus a half grad alpha up of g mu nu h mu nu nu. Now let me substitute what h nu is in terms of h old. So first we get the divergence of h old. Then we have this divergence of the gauge perturbation. Then we have this second term, minus a half times grad alpha h old. So h old here with no indices is the trace of h old. Minus a half grad alpha of 2 grad mu xi mu. So when this is g mu nu, contracts with this derivative of xi, you just get the divergence of the vector xi. Okay, so let me combine this term with this term. Write that as just the divergence of h bar alpha beta old. Now this term here, I'm going to use the Ricci identity again. So we have grad beta, grad alpha, xi beta. So I'm just moving this index up, this index down. And that is grad alpha, grad beta, acting on xi beta, plus r beta, gamma, beta, alpha, xi beta. So that's just commuting this derivative at the cost of introducing a Riemann term. And you see this is actually the Ricci tensor because we're contracting two indices inside the Riemann. So this is 0 in our vacuum background. And this term here, we have grad beta contracted with grad beta, and that's just the box operator. So we have the box operator of xi alpha, and then we have this final term, minus grad alpha, grad mu, xi mu. And you can see that this term here is going to exactly cancel this term here. So that cancels that. And so all we're left with is this box operator and this divergence of the old trace-reversed metric perturbation. So we want this whole thing to equal 0. So this equals 0 if the box of xi alpha is equal to minus the divergence of h bar alpha beta old. So whatever gauge you started with, you just take the divergence of the trace-reversed metric perturbation, and then you just solve this equation. And this is a hyperbolic equation, so it always has a solution in at least a nice patch of space-time. So we can always solve this. Which means we can always transform to the Lorenz gauge from whatever other gauge we happen to start in. Okay, so now we're just going to look at the Lorenz gauge field equation, which is the box of h bar alpha beta plus 2 times Riemann alpha mu beta nu h bar mu nu is now minus 16 pi T1 alpha beta. So that what was an 8 pi has become a minus 16 pi because we've just multiplied this minus a half to the right-hand side of the field equation. So the left-hand side we have there is not the linearized Einstein tensor, it's minus 2 times the linearized Einstein tensor. So this is the equation we want to look at. And we're going to start looking at it by considering a point-particle approximation. So we want our small object to be very, very small compared to the big object and compared to the radius of curvature of the background spacetime. And so you can imagine, at leading order, we can think of it just as a point, because it's so much smaller than everything else around it. So we're going to start by approximating it as a point particle. Later on in the lectures, we're actually going to derive the validity of this approximation. This is actually something you can rigorously derive, that this is valid at linear order. So the point particle approximation is that the stress energy tensor is the mass of the small object times an integral of the 4 velocity. So u here is dz alpha d tau, where z is the coordinates on the world line gamma, and tau is proper time as measured in the background spacetime. And this gets multiplied by a delta function. Four-dimensional delta function. And on the bottom, we have square root of minus the determinant of the background metric. It's an integral over proper time. So this may be a little bit funny looking at first. So why do we have an integral in our point particle stress energy tensor? Well, let's go into a local coordinate system to see what it looks like there. So say this is your world line. Let's just define coordinates xa to be coordinates orthogonal to the world line all the way along, and then take proper time tau as your third coordinate, or sorry, your fourth coordinate. So we can use tau and xa as coordinates and then evaluate what that stress energy tensor comes out to be. So this is a co-moving coordinate system near the particle. So in that case, T1 alpha beta is m times delta tau alpha delta tau beta. So the 4 velocity on the world line is just 1 in the tau direction and 0 in the spatial directions. Now let's write out this 4-dimensional Dirac delta as the product of a time delta and a 3-dimensional delta. So it's xa minus za in the argument, but za is 0 because we've defined the world line to be the origin of this local coordinate system. But now we can just evaluate this delta function. So now we just have m times delta tau alpha, delta tau beta, times this 3-dimensional delta function. So this is what you would expect for a point particle. It's just a delta function at the spatial position, or supported at the spatial position of the particle, multiplied by the mass. And this is a local coordinate system, so it's essentially just the TT component, which is, remember, the energy component of the stress energy. So this is just the energy multiplied by a delta function at the particle's position. So that stress energy tensor we wrote over there makes perfect sense. Okay, so later on, I'm going to come back to this approximation and show that it's actually correct at first order to say that the stress energy tensor is this point particle. And that's true even if the small object is a black hole, so it's actually just a vacuum, vacuumetric. Still, at linear order, you can treat it as a point particle. But for now, I'm going to take as a given that we want to solve this equation with a point particle source. Now let's just assume that the motion of that point particle satisfies equation of motion of the form that I wrote down yesterday, where you have the covariant acceleration equal to some first order term plus some second order term, and so on. So again, we'll justify this properly later on, but you can think at leading order, this point particle is just a test particle. So at leading order, it has to be moving on a geodesic, so you don't have any zeroth order term in the acceleration, and you just have corrections coming from the gravity of the gravity produced by the small object. Okay, so again, at leading order, this is just zero. So let's start by analyzing geodesics of relevant spacetimes. And once we know how geodesics look, we can then think of putting a geodesic orbit into this stress energy tensor and solving for H1. From that, calculating what the self-force is, and then evolving the orbit away from the geodesic motion. Okay, so let's start in Schwarzschild. So geodesics in Schwarzschild spacetime. So the physically realistic case of an emery, the big black hole is going to be rotating. It's going to be a Kerr black hole. But let's just start with a simpler case where we assume the central black hole is non-rotating. So in Schwarzschild coordinates, I'm going to write the metric as minus f dt squared, where this f is 1 minus 2m over r, plus f inverse dr squared plus r squared d omega squared, where this is the metric on a unit 2 sphere. Now, remember that if we have a killing vector, so here z is not a gauge transformation vector, it's a killing vector. So if we have a killing vector of our spacetime and a geodesic world line z, then we get a conserved quantity. Given by u alpha contracted into c alpha. So this is a conserved quantity. It's constant along the world line. So for simplicity, let's put ourselves on the equator. We can always rotate our coordinate system to put our geodesic on the equator. And then there's two relevant killing vectors. This is independent of time, so we have a time-like killing vector. And it's independent of phi, so we have an azimuthal or axial killing vector. So we have two killing vectors that are relevant here. Right, the first one is c alpha with a subscript t, which in Schwarzschild coordinates is just 1 in the t direction, 0 in every other direction. And this means the orbital energy E equals minus U alpha, xc alpha, t, means this is constant. Then we have our axial killing vector, which I'll write as xc alpha with a subscript phi. And that's just 1 in the phi direction and 0 in every other direction. So that gives us another constant, which is the z component. So not z as in z alpha, but z as in orthogonal to the equatorial plane. Z component of angular momentum of the orbit is conserved. So this is Lz, which is U alpha contracted into xc alpha phi. So now you can also just write this as minus ut, and this is just u phi with indices down in both cases. So this is constant. So for a general orbit that's inclined, you'll also have a constant x and y components of the angular momentum. But we're going to just put ourselves in the equator, and so these are the only two relevant quantities. Lx and Ly are just 0. Okay, so let's write down the parametrization of an equatorial orbit, and then use these constants of motion to solve the geodesic equation. So we can parametrize our motion as t is a function of tau, r is a function of tau, pi over 2 for the theta component, and phi is a function of tau. So obviously this is completely general except for the fact that we're putting ourselves on the equator. But now we have the dt d tau, which is ut with index up, is equal to gtt times ut with index down. This is minus F inverse. This is minus the orbital energy. So this whole thing is just F inverse E. Let's write that as T dot. So dot here means derivative with respect to proper time. T dot is E over F. Just write that out explicitly. U alpha, I'm writing as T dot, R dot, 0, phi dot. Okay, doing the same thing for the phi component. D phi, d tau is U phi, which is G phi phi, index up, U phi, index down. So on the equator, G phi phi is just R to the minus 2. The sine theta evaluates to 1. And now it's times Lz. So we've got an equation for T dot and an equation for L dot. And we also have one more constant of motion, which is the conserved length of the 4 velocity. So we also have that G alpha beta times U alpha U beta is -1. So this is true at all points along the orbit. It's just using the normalization with the proper time. So here you'll have a term that's t dot squared, you'll have a term that's r dot squared, you'll have a term that's phi dot squared. So I'm just going to solve for the r dot term. We have r dot squared is f times -1 plus f t dot squared minus r squared phi dot squared. We can write that as e squared, replacing this t dot squared with e, minus f times 1 plus lz squared over r squared. I'm going to call this whole thing v of r, which is an effective potential. Okay, so we're interested in bound orbits that spiral inwards rather than orbits that just come in, get scattered off the black hole, and leave back to infinity. So we're interested in orbits that oscillate between a minimum r value and a maximum r value. So we want oscillations, or it could just be at a fixed value of r, a circular orbit. We could replace this with bound behavior. Now, turning points, you can see, are where r dot is equal to 0, so that's where e squared is equal to v. So we have r dot equals 0 at e squared equal to v. Now let's parametrize the orbit in a Keplerian type parametrization. So parametrize with kind of Keplerian parameters. In particular, the eccentricity and the semilattice rectum. So the eccentricity is r max minus r min over r max plus r min. So for a circular orbit where r max is equal to r min, you just get 0. And the semilattice rectum is P equal to 2 times R min, R max over M times R min plus R max. So this is telling you how far away from circularity you are, and this is telling you basically something about the radius of the orbit, the average radius of the orbit. Okay, so if we solve these two equations for R min and R max, in terms of P and E, we get that R min is equal to P M over 1 plus E, and R max is equal to P M over 1 minus E. So here you see if the eccentricity is exactly 1, R max is infinity, so that's the case where you actually just go all the way out to infinity, never come back. So note that E is always between 0 and 1. So now we take these parameterizations, put them into this equation, and solve for what R max and R min are in terms of E and LZ. Or put another way, This is our min or our max. We plug these expressions in here, and that gives us equations for E as a function of P and E, so capital E as a function of P and E, and Lz as a function of P and E. So V depends on Lz, E is just E, and then we're writing our min and our max in terms of little p and E, and so then we have an equation for, well, two equations, one at our min and one at our max. So then we have two equations for E and L we can solve as functions of little p and little e. So then we've replaced everything with little p and little e as our parameters instead of capital E and L. Now we want something that's oscillatory, so let's write down an oscillatory parametrization for the radius. Let me introduce just a phase variable psi. So we know that r is going between Pm over 1 plus e and Pm over 1 minus e. So all that's changing is the factor in front of this e on the bottom. So let's keep the Pm upstairs. Let's keep the 1. And then we have e times an oscillatory function cos psi. So this is going to oscillate between minus 1 and plus 1, just like we want the oscillation between our min and our max. So in the Keplerian case, we would actually have that psi is equal to phi. Well, modulo some details. But if psi was equal to phi, then this parameterization would just be an ordinary ellipse. And then P and E would have a geometrical interpretation. So if this is A, the semi-major axis, then this distance here between the center and this focus is A times E. And this distance here is P. But we don't have this for geodesics in Schwarzschild. What we actually have is d phi d psi is equal to d phi d tau, which is just phi dot, times d tau dr, which is 1 over r dot, times dr d psi. So this is just a sequence of chain rules. So if we substitute phi dot and 1 over r dot, and we just take a derivative of this with respect to psi, what you find is that d phi d psi is square root of p over p minus 6 minus 2 e cos psi. And this is always bigger than 1. So phi is always increasing faster than psi. So what that means is you don't have an ellipse, you have orbital precession, where in one radial cycle, you complete more than one azimuthal cycle. Psi goes to psi plus 2 pi. Then you go through one full radial cycle. R goes from, say, R min to R max back to R min. But then phi goes to phi plus some number delta phi, where this is strictly bigger than 2 pi. So what that typically means for a typical orbit is you have precession. So rather than coming back to the same point at a radial cycle, we have, say, something like this. So that's a pretty typical case. But then you can get extreme cases called zoom whirl orbits, where you come in and you complete many, many, many phi cycles for a given r cycle. So you come in, you zoom in, you cycle around and around and around and around and around, and then you come back out. And so on forever. And you can arrange your P and E to make the number of whirl cycles arbitrarily large. So you can make it, you can actually make it come in and just keep whirling forever before it comes back out. Okay, but now a key thing here is this means we have 2 frequencies, or 2 periods. One for the radial motion and one for the phi motion. So we have a radial period, TR, and an azimuthal period, T phi. In general, the orbit is not closed. Meaning you get what I've drawn, where it just keeps cycling around and never closes back in on itself. But if you make a certain arrangement between the 2 periods, then you can get a closed orbit. But if nr tr is n phi t phi, or these are both integers, so nr and phi are both, say, positive integers, then the orbit is closed. So as an example, if the radial period is twice the phi period, then you get 2 cycles of phi for 1 cycle of r. So that'll look like that. All right, so this was all in Schwarzschild. Now let's move on to Kerr. Any questions about this before we go to Kerr? Okay. So we're going to do something very similar in Kerr. But there, the motion is not going to be confined to the equatorial plane. And we're going to have a constant of motion that is not associated with a killing symmetry, and it's not associated with conservation of length. It's going to be associated with what's called a killing tensor. So I'm going to write the metric explicitly, but I'm going to note that to do the question on the exercise sheet, you do not need to know anything about the explicit form of the metric. So this is in a coordinate system called Boyer-Lindquist coordinates. The coordinates are again t, r, theta, phi. But the metric is obviously much more complicated than the Schwarzschild metric was. Really, the key physical thing is this cross term between t and phi. So in Schwarzschild, you don't have any mixing of space and time components of the metric. You have a pure time component and you have pure spatial components. In this case, you have a mixing between them, and that corresponds to the fact that your metric, or your big black hole, is rotating. So this parameter A that appears here is the spin angular momentum of the big black hole divided by its mass. So that's the spin angular momentum, and this is called, A is called the spin parameter. Let me just write out what those sigmas and deltas are. So you sometimes see the same symbols, sigma and delta, meaning different things. In this case, sigma is r squared plus a squared cos squared theta. Delta is r squared minus 2mr plus a squared. Okay, now this metric only has two killing symmetries. Schwarzschild had more because it was rotationally invariant. But this one, you can actually read off the killing symmetries just by looking at what coordinates the metric is independent of. So here we have two killing vectors. You can see that the metric is independent of t, which again, like in the Schwarzschild case, means that we have a time-like killing vector xi alpha t, which is just delta alpha t. And it's also independent of phi. So we have an azimuthal killing vector, or axial killing vector, xi alpha phi, which is just delta alpha phi. So these are the same two we looked at in Schwarzschild, but in Schwarzschild we also had additional ones that allowed us to stay in one single plane, because we could just set Lx and Ly to 0, and we stay in one plane, because Lx and Ly stay constant. In this case, we do not have any additional killing vectors, so we cannot put the orbit generically in a fixed plane. You can just choose an orbit that stays in the equatorial plane, but that's not a generic orbit anymore. You don't have the freedom to put every orbit in the equatorial plane. Most orbits are going to come off that plane. So this, again, goes to two constants of motion. E is minus ut down. Lz is u phi down. But then additionally, you have a hidden symmetry. Associated with a killing tensor. So I'll write k alpha beta is 2 sigma L alpha L beta plus r squared g alpha beta, where L alpha is an outgoing principal, got too many L's here, it's n beta L alpha. So L alpha is an outgoing principal null vector. So for this purpose, all you need to know is that it's a null vector going away from the black hole. N alpha is an ingoing null vector. So it's easy to see these are ingoing and outgoing by taking the Schwarzschild limit where A goes to 0. Or even better, take the flat space limit, where A goes to 0 and capital M goes to 0. Then you get L alpha is just 1, 0, 1, 1, 0, 0. So that's just a vector pointing radially outward like that. 1 to the right, 1 to the up. And N alpha is a half minus a half, 0, 0. So this is L alpha. And this is N alpha. Null vectors pointing outward and inward, respectively. Okay, I just want to say one more thing about what you get from this hidden symmetry. So in analogy with Killing's equation, which was grad alpha c beta symmetrized is 0, for this Killing tensor, we have grad alpha k beta gamma is equal to 0. So symmetrized over all three indices now. So one of the exercises was to show that given this, you have a conserved quantity given by k alpha beta, u alpha, u beta. This is constant along the geodesic. And this constant is related to the orbital inclination. So this constant is 0 if the orbit is on the equatorial plane. This is called the Carter constant. There's also another thing that's not C, but is also called the Carter constant, which is C minus Lz minus AE squared. These are both called the Carter constant. They're both constants because if C is constant and Lz is constant and E is constant, then Q is also constant. Okay, so tomorrow we'll use this to solve the geodesic equation and learn some about geodesics and Kerr. Okay, questions? Nothing?
Slow variation of the constants of motion.
Mm-hmm.
So doing a similar thing would give us a measure of the momentum of the gravitational waves emitted.
So doing the same thing is called the adiabatic approximation. So that's exactly the approximation I was sketched yesterday in the exercise in the tutorial. So that's where you have the constants of motion slowly changing with time.
Yes.
Yeah. Okay. So for E and L, the slow change in the orbital energy and orbital angular momentum is exactly equal to the flux that leaves the system. So that includes the flux that goes to infinity, but also the flux of gravitational wave energy that goes into the big black hole. For the Carter constant, no one knows of a flux of Carter in the gravitational waves. So for that one, you don't have that kind of balance law.
So there's no simpler way to do that, like other than solving the Killing's equation with perturbed metric components, higher order perturbed metric components.
You mean
to calculate
H alpha
the
beta?
corrections to the Killing vectors and to obtain variation in constants
So
of
if you're looking at equatorial orbits, then you don't need to go through all the details of calculating the first order force. You can just say, okay, I've got a balance between energy leaving and the change in orbital energy. And similarly, you have a balance between the angular momentum leaving and the change in the orbital angular momentum. And you still need to know what H1 is, but you only need to know a specific part of it, which is the wave content at infinity and the horizon. For the Carter constant, because you don't have a balance law like this, you actually need to know, okay, what is the self force in terms of the metric perturbation, and derive the average rate of change, say Q dot average, from the average of the force. So I mean, in a generic asymptotically flat curved space-time, you can still derive the Bondi mass loss formula, for example. In this lecture, it's no. I'll just use the balance law, taking it as a given. So I mean, because you need to go to higher order to do what we need to do, I don't think there's too much, you don't need to spend too much time thinking about the balance law because it doesn't give you all the information you need.
Last one.
Yeah.
So when one solves for geodesics in the Kerr space-time, the Carter constant facilitates a separation of variables between theta and the phi coordinates.
Yeah.
So if the Carter's constant is considered to be varying, then probably we can interpret that as the motion no longer being localized to the orbital plane. I mean, it can roam around.
Yeah, so you can look at, I got this written down. So you can look at what this is in flat space-time to get some idea of it. Not even flat space-time, Schwarzschild. So if you take the a goes to 0 limit, then this is Lx squared plus Ly squared. So that tells you exactly about the inclination away from the orbital plane. C in that limit is just the total angular momentum squared. So this can give you some idea of what it means physically. What is K alpha beta in Schwarzschild? So you just go back here and set A to be 0 in all these quantities. So this becomes r squared over delta. And delta is now r squared times f. And there's got to be something related to the killing vectors that exist in Schwarzschild. But I don't know offhand what the formula is.